Right, footfall. What is footfall first of all? Now, footfall itself is a prediction really of how lively the floor or structure is going to be when people walk on it. Now, when people think of sort of vertical sort of vibrations from people walking, even 10 years on, a lot of people think of is the Millennium Footbridge. Now, we're not looking at this particularly because the Millennium Footbridge was a horizontal footfall problem, which is, I'm going to say, being quite rare. With GSA is what we do with GSA is look at the vertical footfall vibration, which actually occurs in all structures to a greater or lesser extent. Now, if you do want to know more about the Millennium Footbridge and exactly what was going on there, there was some papers published in the Structural Engineer, which I'm sure we can get hold of for you if you're interested. So, footfall itself. I mean, first of all, you need to look at vibration of the structure. Now, whenever people walk on the structure, every time they put the foot down, or it impacts on the structure, creates a force, and because people tend to walk at a given pace, you get a regular series of impacts which then make the structure start to vibrate. Now, so to understand how the structure vibrates, you first need to find the way the structure wants to vibrate, which is the modes of its vibration. And whilst it's quite simple to find the first mode for a single beam, for a whole floor, it's quite difficult to do this by sort of hand calculation methods, and FE is really the way forward. Now the response to the floor is dependent on a number of things. First of all, there's the frequencies, but also the most important thing is the thing called the modal mass. Now, the modal mass is it's related to how much of the floor is actually moving in the various vibration modes. Now, if you take the first mode there, the mass of the beam, let's say, is 1. The modal mass of that beam under the first mode will be half. You can think of it sort of as the area under the curve, if you will. And the modal mass for the higher frequency modes tends to get less, and so on. Now, because force equals mass times acceleration, or acceleration equals force over mass, the accelerations we're getting are really dependent on how much mass is being mobilized for particular vibration modes. Now, this means that when you have multiple spans, multiple bays, a particular vibration mode will tend to have quite a large mass, which will then resist the vibrations, whereas small areas such as isolated bays can have quite low modal mass, and therefore can have quite high response. So there is a fallacy you sometimes hear that isolated bays do not have a problem with footfall vibration. Unfortunately, quite the reverse is true. And likewise, if you look at the frequencies, as you know, we need to do a structural analysis. The usual requirement is to have a minimum frequency on the floor for the fundamental, but this is only in the first stage, because a large floor or a large span can have quite a low natural frequency, but it has a large modal mass, so it can resist a footfall. Likewise, a short span can have a high frequency, but with a low modal mass can have a high footfall. So there's not a direct relationship between frequency and response. It's quite a complex interaction. Now, to help you help us assess the footfall vibrations, there are a number of design guides out there. One of the first was the American Institute of Steel Construction's guide, which came out about 15 years ago, I think now. Then there was the Arup method, which was published by the Concrete Centre in their design guide for footfall induced vibration structures. That covers all types of materials. And then soon after that, the Steel Construction Institute published their guide as well, and there was a recent revision to that, which is covered in the GSA software. Now, both the AISC and the SCI methods include what we call simple methods for an analysis. That this means for your given floor, you need to assess an equivalent typical bay, and then work out the first couple of frequencies. Now this of course assumes that your structure is similar to the example structure, which it might be, but it's, let's face it, regular structures are quite unusual, and so there's an awful lot of assumptions being built into the simple methods, and thus the answers you get out could be very conservative or they could be very unconservative, and it's very difficult to know which way they go. So both the Concrete Centre and the Steel Construction Institute recommend that you should actually use the FEA method, so do a final element analysis of your structural floor to get the accurate results and accurate predictions of how the structure is going to predict how it's going to work. And the way you model a floor, well, this is a GSA screenshots. This is a composite floor where we have the beams offset down, the slabs offset up, and because these are working together, this will automatically induce composite action in the structure for a composite floor. If it's a non-composite, then that will be inappropriate. You also need to look at restraints as well in the structure. Footfall is unusual because normally the perimeter structure supports the cladding, but under footfall vibration it's the other way round. It's the cladding supports the structure. Likewise, pin connections in steelwork are modelled as fully continuous because the strains are so small with the vibration, then the joints are not actually mobilised. So what we're getting out of it, velocities and accelerations. Accelerations is the main thing. Velocities come about as a part parcel of that, and design guides then need you to look at the end acceleration, whether it's percentage gravity or it's in relation to the what they call the R value. The R value is based on the base curve for human perception of vibration, and the response value of 1 is that the limit of perception. Response value of 2 is twice that, and so on. Now, the R value you're looking for varies depending on what the building or the structure is being used for, because people in different situations are more or less sensitive to the vertical vibration. Now, somebody standing or even walking is sort of least sensitive. Somebody sitting down, more sensitive. Someone lying down, most sensitive of all. And also, of course, people's expectations vary as well. If you're on a floor, people expect that to be solid, but if you're walking on a footbridge, then people are aware of walking in open air and therefore are more accepting of a certain level of vibration. So your actual target values varies from structure to structure and your client requirements. Some clients, of course, have very stringent requirements, such as hospitals and laboratories, where you have to achieve some very tight vibration requirements. So let's have a look at this in action. Right, let me find GSA. First of all, now to save time, I've generally got models I prepared earlier. This is an example model. What we have here is a steel framed building with a concrete slab. So the first thing we need to do is, whilst we could do a static analysis on this, we need to make sure the offsets are set up for this structure. Now we have in GSA a tool for applying offset to beams. Notice the beams are all differing sizes, so I just select all those. I am going to use the tools to apply offsets and offset the beams down to line with grid planes. Now, just in case you're wondering, the webinars are being recorded, so if you miss anything, we'll be able to catch up. Now, yep, everything. So all the beams are offset down, so the top steels are lining up. I now need to select all the slabs. I'll use the find command for this, because I happen to know their property area 1, and they are 160 thick. So I'll just modify those, apply offsets, and I'll just offset them up half a thickness, so 0.08. Copy that. Okay, wonderful, that looks good. Right, so offset done. We also need to set materials now. For steel, I mean steel doesn't change much under proper steel don't change much over time, but whereas concrete is a time dependent material and vibrations occur over a very short period of time, so we need to create, rather than standard concrete, we need to create a dynamic concrete material. So in our materials I shall base it on a typical concrete grade, and then I can modify this using our dynamic code concrete properties. Now in this particular case, the requirement was for a lightweight concrete slab, and I shall then go and assign my slab properties to this this material. Now the overall depth of this is 160 mm on a trapezoidal decking. So to compensate for that, to allow for that effect, I've reduced the bending thickness, and I've also reduced the in-plane factor to give the correct values. Now the in-plane factor will also reduce the self-weight of the slab as well, and the bending thickness will reduce the stiffness of the slab under bending. We also need restraints. If I go, let me set up the first of all the columns. Now these columns are stub columns. These are half the height of the floor to floor. If I modify those, I can just pin them, because essentially the half height will model half a vibration mode of the columns. You notice the beams are broken up to time with the slab, but the columns are not, because we're not too interested in the column vibration, but more the how they stiffen the slab up. Now we also need to set up cladding restraints, and I'll just reduce the display of the cladding down to display the model down to just the slab. And if I switch the nodes on, and I'll select those edge nodes, and I'm going to modify those so they are restrained in the Z direction, but also in the X, so just restrain those in the plane of the cladding. And likewise, these edges here, modify Z and Y this time. And you see we haven't restrained around these openings, because they are openings. Openings tend to have a vibration problem because they have a free edge and therefore low mass. Now for the loadings, self-weight is calculated automatically by the modal analysis, but I need to create some face loads. In fact, I have done already, and I've already got my permanent and variable, or dead and live loads already programmed in here to act on the face of the slab. So there's my permanent or dead loads and my live loads ready to go. Right, I think this model is ready to go for analysis. So let's do a modal analysis first. I just do a modal first. I'll just do a single mode to begin with, just to make sure it's working right and get an idea of the how it's working, and also add in my loads which will add mass onto this structure. Now, taking the full dead load and 10% of the live load. This is a typical value for Footfall. Higher live loads will of course push the frequency down, but they'll also resist the vibration more. So it's sort of a typical value to take. You might wish to do a number of runs with different values of live load to check for sensitivity. Okay, and let's analyze this. Okay, that's worked. And let's look at both the shape and so there's our first mode, coming in at 6 Hz. So this is a low frequency floor. Walking speed is generally up to about 2.5 Hz. High frequency floor starts at 4.5 times the walking frequency, so 10-12 Hz and above. So this is good. So what we need to do now is find all the modes up to 15 Hz. So I'll just erase those results and then go and edit that analysis task. I'll just give it a name and say, not quite sure how many modes, let's say 30 modes, not quite sure, but I will ask for an upper cutoff level of 15 Hz. This is a new feature in GSA 8.5 that you can restrict the frequencies. And let's analyze that. Just takes a few moments. Okay, nearly there. And done. Right. Now, well, we asked for up to 30 modes, but up to 15 Hz, and you see it's actually GSA is calculated up to 22 modes. Found it's well, the 23rd mode would have been a higher frequency than 15, and therefore it's only saved us these 22 modes. Now we have these modes. We can now do a second analysis, which is the Footfall response. And it takes the modal analysis, and we then have a choice of how we excite the floor. Self-excitation usually finds the worst values, and what this does is it applies the Footfall excitation or dynamic loading function at each node, and then measures the response at that same node. Whereas full excitation, whether rigorous or fast, again excites each node but measures the response at all the other nodes, as we see here. And for the full detail, I should go for a fast analysis, fast full excitation. Damping for floor varies. This floor is going to be between 2 and 3% for a typical office. We have number of footfalls to do with resonant response, when footfalls build up over time, and we also have the various design guide functions in here with the Arab or concrete center methods, the SCI and the AIC methods, whether both floors and stairs. And I shall come back to the staircases later. Minimum maximum walking speeds, depending on the usage. I'll leave it as the maximum at the moment. and let me just analyze that. There's mode. Okay, nearly there. Done. So let's switch off that, change results to look at. Now then, the footfall response for a typical office block, looking at value of 8, and in this particular floor we're getting values well over 20, so this floor generally has quite a vibration problem, and it will need some sort of work on it so it will meet the footfall requirements, maybe by changing it from a lightweight to a normal weight concrete, or by other methods, which is something you can then work on. Now this is a steel floor. I just minimize that a minute. What we also could do is call up a similar flat slab model. Now this is exactly the same geometry, but with a flat slab instead. Now with a flat slab, with the concrete, the stiffness very much depends on the reinforcement in the slab as well. So I have my loads already set up, and what I will do here is do an initial analysis of a static load, and what I'll do is I'll just add some analysis cases. So serviceability limit state, which is dead and alive, and just 10% alive, and also a ULS case, which would be 1.35 dead and 1.5 live. If we analyze these, we'll see what we actually get if we go to our well, it's going to be ultimate limit state case, deflection of the slab, and also if you look at moments and torsion, we are getting round about mid-span moments up to about 150, hogging moments. Well, let's change this to actual values. See the worst case of the value. Okay, hogging moments about 300 or so. Obviously there's peak moments over the columns, and mid-span moments of about 110 at ULS. Now if we do some design on this, I happen to know with this 325 slab, we would require T20s, no, yes, T16s at 200 sensors to achieve the static analysis. The design requirements in the mid-span obviously higher at the supports. Now if we were to take this slab, we can use ADSEC to calculate the stiffness of this. Right, and sorry about that, there seems to be some wind noise. And so you can see the capacity of the slab running about 110, and the stiffness of the slab is actually quite low. But if we look at the slab under ULS, you see the minimum, mass span moment is now down to about 56. And if I go back to ADSEC and ask for those, so the So the stiffness of this slab is going to be round about 80. Now the uncracked section, the gross concrete section, is of course at just over 100, and we're about 80 for our mode 56. So this slab is going to be running at about 80% of its bending stiffness under vibration. So let us do a new analysis. What I'm going to do now is I am going to add in again my restraints on the edge of the slab there, and the next direction, and modify those edges there, Z and Y, and we then do a modal analysis and so on this. So let's do the modal analysis. Again, I'll just ask for number of modes and add in my dead and live. Okay, well that's running. Let's have a look, check the results. Ooh, rescale that. Okay, I'm getting various good modes. I'm liking those. Of course, the results, of course, are not going to be those. They're going to be deflection. Okay, and let's now do a second analysis on that, which is the footfall. And let's get the results. Alright. And let's again look at the results on here. And you see in this case we're getting footfall results just under 5, which is much more acceptable, especially for an office. For a high spec office, you'd be looking for results under 4. And if we were to adjust these contours, let me see, 5, and if we specify 8, 4, 2, 1, 0, and we can see for the high spec office, values anywhere except in the red zone are perfectly acceptable. And maybe if you're looking for higher requirements elsewhere. Now these corners are not actually showing any response at all. The reality is that in these corners they're actually vibrating quite a high frequency and much higher than the 15 Hertz we chose, and you really need to actually look, take far more modes to actually get the detail into these corners. Something to watch out for. Now if you want to look in more detail at the vibrations as well, we can see, look in the output. So if we get our nodal results, and let's look at the summary, and you see the worst node is actually node 257 with a response value there. And if I ask for 257, but also ask for the resonant and transient analysis and just the output tables, we can look again in here in more detail, and we see both the resonant and the transient. Yeah, there is self-excitation on these nodes, and resonant at the highest frequency. Other things we can look at is the chart views for these. So if I ask for the footfall resonant and transient for 257, and first of all, transient analysis, we see these are the various modes which are affecting that location. Mode 4 most affect, mode 6 not quite so much, and mode 5 as well. Mode 2 has no effect whatsoever, and so on. So we can see the effects there, the vibration over time, this in transit, the effects of the walking speed on the transient response, and as is normal, as you increase the walking speed, the transient response builds. Resonant analysis, the mode's slightly different this time, but mode 4 again dominating. This is the forcing functions. This is a standard graph, and this is the frequencies against response, and also the walking frequency against resonant response. And again, in this case, the increase of walking speed increases the response, but in a much more extreme manner. So you can see, if you to justify a lower walking speed, you'd see quite a large reduction in the response value. Now this is a flat slab. We can also do post-tension slabs as well. Now the difference here is obviously the slab is much thinner. So 325 rather than 225 rather than 325 thick. But also we also have a pre-stress value on the slab as well. Now for simplicity, I've just taken a straight axial pre-stress force. Reality is obviously tendons are moving around, but for the footfall, in this case, I think we can just take the overall force on this. Now the effect of this pre-stress force is it of course puts the slab into compression, and the compression load can reduce the stiffness of the slab, because mentioned sort of musical instruments, if you tighten a string up, put tension onto a string, the frequency increases, and likewise with structures, if you put tension on, the frequency increases, you put compression on, the frequency decreases, the stiffness decreases. And we can account for this by, rather than just a modal analysis, a modal P delta. And what this does, again, if I just take my 30 with an upper frequency of 15, and again my variable and permanent loads, but we also have the P delta load, which is the pre-stress load on the slab, and this loads up the structure and affects the stiffness accordingly. And the end result of this will be to reduce the frequencies of the slab, and possibly then for induce more frequencies. And of course, PT slabs tend to have more of a footfall problem because they are much lighter than flat slabs. So, with our analysis done there, let's do a new analysis of the footfall. Again, fast, take 2%, analyse that. Now remember, the flat slab was coming in just under 5, response value 5. The response value here no results, much higher. Actual values. Response value of 14 in that location. And again, if I specify these, so 16, 8, 4, 2, 1, 0. Yeah, we can see that in this particular case, even though the flat slab or the PT slab is structurally more efficient, because it's much lighter, it's much more lively as well, and therefore giving a much higher response. So most of the floor is okay for high grade office. There are areas of the floor which are okay for standard office, and some bays around these openings which the occupants would find quite lively unless they were restricted to sort of service or sort of reception type areas or so on. Now this is looking at vibration over a whole slab. You can also look at quite narrow areas and the effects on that. So let me just imagine if you were you had something like an operating theatre or something like that, which you wanted to look at the effects of vibration of, you know, let's say an operating theatre. Operating theatres, people walk around quite slowly, but they're very sensitive. But people walking outside the room can be walking corridors and therefore walking quite quickly. And so if we take, okay, I mean this particular floor won't do very well, I know, but if I create a list of that and call it, do I have my lists in here already? Nope. Okay. So this area here, I'm going to call this my operating theatre, and I can look at the response elsewhere. So I'll do a new analysis task. Theatre. Response nodes is the theatre. Excitations all. Well, actually, if I set that to theatre and edit that, all not so. No. Right. Operating theatre 2%. Walking speed about 1.8. Analyze that, and then do another and again a fast response is the theatre. Excitation this time all. So excitation exciting people walking outside the operating theatre, and walking speed corridors 2.2 Hertz. So we have the answers. Let's have a look at the numbers. So the people walking within the operating theatre itself, actually rather than the contours, let's do the individual nodal results. People walking within the operating theatre, okay, 2.5 R value, too high really. And for people walking outside the operating theatre, get up to nearly 6. So people walking outside the theatre is the governing case. I mean, let's face it, putting it next to an opening is going to be a bad location anyway. But the principle is there. Now, obviously, these are building examples. We can likewise do bridges. Here is one I prepared earlier, and this is concrete three-span bridge. You might recognise this from the Concrete Centre guide. And what I'll do here, I will run some analysis. Now I know from checking previously that 3 modes will be sufficient for this. Self-weight is all in there already. Bridges, staircases might not take any live load. I'll choose not to in this case, so maybe just 1 or 2 people walking across. And what we then get is first frequency of 5.5, 7, first frequency 18, so that's strictly speaking outside our 15 Hertz range. This is quite a chunky concrete bridge, so if we do the rigorous damping is again going to be low. We analyze this, and the response that we get. Now, bridge responses can be quite high. We're actually getting response about 4, so probably nothing that people will notice at all. Bridges you can get over acceptable vibrations are over 30 or so, but this is quite a chunky concrete bridge, so this will be fine. I also mentioned we can do staircases. Now staircases have the problem that one, they are very, very light, and secondly, that when people are walking up and down stairs, the impact forces are much higher and they're walking faster as well. Now this is a staircase model. Now no cladding on this, but obviously the balustrading can have kind of effect on the vibration of a staircase. So let me do a new analysis on this. Let me just check the modal. No additional loads. And this is high frequency, that's 17 Hertz. So let's delete the results, analyze that, and ask for, I don't know, 20 modes, but with upper frequency, 17, let's go up to 35. Make sure we get, as it happens, only the first 3 modes are suitable. Now I have set up a list of the tread nodes already, and these treads, this is where people are walking, this is where the response we felt. We're not interested in the vibration of the balustrading itself. So I'll do a new analysis task on this, which is a footfall. The rigorous analysis, but we're only interested in the response and excitation on the treads themselves. Damping, and this time we pick up the staircase methods. Now the staircase methods, you notice the walking speeds rather than maximum about 2.8 or so, maximum speed of 4.5 Hertz. People can run up and down stairs quite fast, and of course the impact forces are much larger as well. And in this particular case, the response that we get is what am I doing? 30, which might just about be acceptable depending on how the staircase works. Right, I think that just about gives you a whistle-stop tour of footfall analysis.